I wanted to solve a problem involving projectile motion. So this is a problem about a basketball shot. We're told that the basketball is thrown into the hoop. We're told that the horizontal distance from the location of the shot to the hoop is 8 meters. We're told that the vertical distance from the location of the shot to the hoop is 1.05 meters. We're told that the basketball is thrown at an angle 40 degrees above the horizontal. And we're asked to figure out the speed that the basketball was thrown at to make the shot. And so I pictured that situation here. So this curve is the trajectory of the basketball from where it was thrown down here to where it reaches the hoop over here. And you see horizontally the distance is 8 meters. You see vertically the distance is 1.05 meters. So I've called that horizontal displacement, x minus x naught, the difference between the final and initial horizontal positions. I've called the vertical displacement, y minus y naught, the difference between the final and initial vertical positions. And then I've marked over here on the left-hand side, the angle at which the shot was made, 40 degrees, we know that. The speed at which the shot was made, we're going to figure that out. And so that's our task here. And this is, quite a sophisticated problem, quite a tricky problem, and we're going to work our way through this. And it's going to take us a few steps. So the first steps that we're going to do is to write down equations for the horizontal displacement of the ball for the trip in terms of the speed that the ball was thrown at. We're going to write down an equation for the vertical displacement of the ball for the trip in terms of the speed that the ball was thrown at. And then based on those equations, we'll solve for the speed. And what we're going to discover is we're going to get two equations from the horizontal motion and the vertical motion. And those two equations will be two equations with two unknowns. One of them is going to be the speed. And so we're going to solve the two equations for the interesting unknown, the speed. And so there's a physics part of this problem, which is kind of setting up the equations for the horizontal displacement, the vertical displacement. And then there's a more mathematical part of this problem in which we solve two equations involving two unknowns for an interesting unknown quantity. Okay, so let me start by writing down the equations that describe the horizontal displacement and the vertical displacement. And so I'm going to put these two equations downstairs here. And let's start with horizontal. And I'm going to start by just sketching out the horizontal motions. So this path of the basketball is a parabola. It's a curve in two dimensions, in x and y. But if we would just see the horizontal motion, it would just be simple left-right motion. And we know some things about this motion. We know the displacement for the trip. We already wrote this down. I'll write it down again. It's 8 meters. We know the horizontal acceleration. We know that in projectile motion, there's actually 0 horizontal acceleration. It doesn't speed up or slow down horizontally. We don't know the initial horizontal velocity because we don't know the initial velocity. But we do know that initial horizontal velocity is the initial velocity times the cosine of 40 degrees. So cosine of 40 degrees times the velocity here, or the speed here, will give us the horizontal component. So we don't know that. We do know, of course, that the final velocity, I'll call it Vx, is the same as the initial velocity because there was no acceleration. And so that's a picture of the horizontal motion. So using this picture, I can write down an equation for the displacement, that's x minus x naught, in terms of the initial horizontal velocity, and the elapsed time. And if there was an acceleration, there would be a 1/2 at squared here as well. But in this case, there's no 1/2 at squared because there's no acceleration. So this is I'm just using one of the equations of motion, the one for the displacement, and applying it to the horizontal motion. Let's do the same thing for the vertical motion. And let me make a little sketch of the vertical motion. The basketball goes up and then down and goes into the hoop. So that this is sort of a picture of the basketball's upward and then downward motion into the hoop. And we know a number of things about this motion. Let me write them down. So we know the displacement is 1.05 meters. That's the difference between y and y naught, the final and initial positions. We know the acceleration. Well, that's the acceleration of gravity. And that's going to be minus 9.8 meters per second squared. And while we don't know the initial vertical velocity, v naught y, we do know its relationship to the initial velocity. It's the initial velocity times the sine of the angle at which the basketball was thrown. So sine of 40 degrees. And so these are the quantities that describe the vertical motion. They're equivalent to the quantities up here that we use to describe the horizontal motion. And now we want to write a similar equation for the vertical displacement rather than the horizontal displacement in terms of the initial velocity of the basketball. And so again, thinking about that equation of motion, there's two terms over here on the right-hand side of the equation. One term is the initial velocity times time. So in that case, that's going to be v naught sine 40 degrees times the time. And then there's the second term, which involves the acceleration. It's 1/2 times the acceleration times the elapsed time squared. So that's plus 1/2 ay t squared. And so that's the equation describing the vertical displacement. At this point, we got two equations. Let me label them. Here's number one. Got it by considering the horizontal motion and specifically writing down the equation for the horizontal displacement in terms of the initial velocity, v naught. And then here's the second equation. This was obtained by thinking about the vertical motion and specifically the vertical displacement. And again, it's an equation for the vertical displacement in terms of the unknown initial velocity. And if you look at these two equations, look at this one I've labeled 1 and this one I labeled 2. Well, we know the displacements on the left-hand sides of both equations. But on the right-hand sides, they both contain two unknown quantities. The velocity, the initial velocity, the v naught, that's an unknown. And the time, the elapsed time, that's also an unknown. And so now we're really faced with a mathematical problem of, we've got two equations with two unknowns, v naught and t, and we want to solve them for the interesting unknown, v naught. So let's do that. Okay, so to solve these two equations for the unknown velocity v naught, the procedure I use, and I'm sure it's not the only procedure, is that I used this first equation. So using equation number 1, I wrote an equation for t by rearranging equation number 1. And so I just divided the displacement by v naught and divided it by cosine of 40 degrees. And I also filled in the fact that I knew the displacement was 8 meters. And so t equals 8 divided by v naught cosine 40 degrees. I then put that expression for t into equation number 2. So I then wrote out equation number 2. So on the left-hand side of it is the vertical displacement. I'm going to put in the number for that. It's 1.05 equals the unknown velocity v naught times sine 40 degrees times time. And I'm going to plug this expression in for time. So if I do all that, I'm going to get 8 divided by, multiplied by tan 40 degrees. So what happened there was, when I substituted in this expression for the time, this v naught in the denominator canceled with this v naught in the numerator. So those two v naughts canceled out. That's why I don't have a v naught here. And also what happened, I had a sine 40 degrees divided by a cosine 40 degrees. And that's just simply tan of 40 degrees. So I get this simple term here. And then I've got a second piece, 1/2 times the acceleration times the square of the time. So for that case, if I substitute in this expression for the time, I'm going to get the following. Expression. So the minus 4.9 is when I substitute in minus 9.8 meters per second squared for the acceleration. And so it's just half of that. And the 8 divided by v naught cosine 40 degrees, well, that's just this expression for the time. And of course, that's squared. And so what I've done here is by combining equations 1 and 2 together, I've made a new equation in which I've eliminated the unknown time. And now I just have only one unknown quantity, is this velocity v naught. And so I've just got to rearrange this expression for v naught. Well, I won't go through the working out, rearranging the expression, but look, you can fill in tan of 40 degrees and cosine of 40 degrees. That's simple. And then you could move the terms without the v naught in over to, say, the left-hand side, and leave the term with v naught in on the right-hand side. And then you could invert the terms on the left-hand side and right-hand side, so that you didn't have a v naught in the denominator, you had a v naught in the numerator. And then you could take a square root of the left-hand side and right-hand side, so you wouldn't have a v naught squared, you'd have a v naught. And if you do that procedure of rearranging this equation here as an equation for v naught, you get the following. Remember, I filled in the numbers for the tangent of 40 degrees and the cosine of 40 degrees. You get that v naught is the square root of 534 over 5.66. And if I quickly work out what that number is here on my calculator, it comes out to be 9.7. 9.7 meters per second. And that's the answer to the problem. So just to summarize, in this problem, we were faced with a basketball shot. We knew the horizontal distance traveled and the vertical distance traveled for the basketball shot. We knew the angle, direction of the basketball shot, but we didn't know the speed of the basketball shot. And so we had to solve for the speed. And so I went through several steps in solving this problem. The first steps are the more physics steps. I analyzed the horizontal motion over here on the left-hand side to write out an equation for the horizontal displacement that we know in terms of the unknown velocity. And so we wrote down that equation. And here is the unknown velocity. We did a similar thing by analyzing the vertical motion. We thought about the vertical motion, and we wrote down an equation for the vertical displacement, the known vertical displacement, in terms of the unknown velocity. Now, equation 1 on its own, we couldn't solve for the unknown velocity. Equation 2 on its own, we couldn't solve for the unknown velocity, because equation 1 also contains the time for the trip that the basketball took. Equation 2 also contains the time for the trip that the basketball took, and we don't know the time. And so what we had to do was this last, more mathematical step over here. We had to combine together the two equations to eliminate the unknown time and just leave behind the unknown velocity. And so that's what I did in this little step here. I basically used equation number 1 to write an equation for time, and then substituted that equation into equation number 2. So I put 1 into 2. That's what I'm doing here. I'm putting equation one, and its expression for time into two. And that gave me a new equation. It's a little bit messy, but that's okay. It's much simpler in the sense it just contains the unknown initial velocity, and everything else is known. And look, I was putting in numbers here to prove to you, to show you that everything else is known. Yeah, here's the vertical displacement for the trip. Here's the horizontal displacement for the trip. And here's the horizontal displacement for the trip. Here's the acceleration of gravity during the trip. And here's the angle, 40 degrees at which the basketball was thrown. So everything is known in this equation except V naught. And so you can simply rearrange it for V naught. I didn't go through the details of that. It's an exercise you want to check you're happy with. It's just rearranging the terms. It's just inverting terms so that you move V naught from the denominator to the numerator and taking the square root. So you've got a V naught instead of a V naught squared. That's all I did to get this expression here and solve for the velocity of the basketball. So that's quite a sophisticated problem, right? This basketball problem is a sophisticated problem to solve. It's a complicated path that the basketball took. It was a parabola. It was moving both horizontally and vertically. But by breaking down the motion into horizontal and vertical parts, by analyzing the horizontal and vertical motion, we were able to figure the speed that the basketball must be thrown at, given that angle that the basketball was thrown at, to make the shot. And it's a powerful proof of our understanding, a depth of understanding of projectile motion.